Hi students, so we begin optimization tutorial 2. In this tutorial, I'm going to discuss the Taylor series and the quadratic forms. These are important concepts in optimization theory. We are going to actually solve some examples related to these particular concepts. I'm Dr. Ganguly. Now in today's video, I'm going to discuss the following topics. So we are going to look at Taylor series in 1 dimension and 2 dimension. Then we are going to put the Taylor series in the matrix form. We are also going to look at the concept of quadratic form and the symmetric matrix A, which is associated with the quadratic form. We are also going to look at the nature of the quadratic form, and this leads to concepts such as positive definiteness, negative definiteness, and so on, which go with matrices but are actually related to the quadratic forms concerned. Also, we are going to look at the indefinite matrix. Now, the companion to this particular lecture is optimization lecture 2, that is the Taylor series and quadratic forms. This is the theoretical lecture, and today I'm going to look at the tutorial, which is essentially solved examples. Now, you can look at my optimization playlist for the full course, and this particular video is also going to be inside that optimization playlist. So let's begin with question number 1, and this is expand sin x in a Taylor series about 2 points, and these points are x is 0 and x is pi by 2. And you are also asked to use terms up to the second derivative. So this is the question. Now let's try to solve this question. Now you have the function here. I'm giving the function in red. Fx is sin x. And we write the equation for the general Taylor series. Now if we take the Taylor series of a function f of x about the point x star, then we can write out this Taylor series as this expansion. Now as you take the different derivatives, for example the first derivative, the second derivative, the Taylor series becomes better and better for most functions. So in most cases the Taylor series is going to converge, and there is this remainder term r which encapsulates all the terms which we have not included here. So here I am only including up to the second derivative term as was asked in the question. Now I need to immediately calculate the first derivative of f and the second derivative of f. Now for the function sin x, this is a simple function, so we know from calculus the first derivative of f is cos x and the second derivative of f is minus sin x. That's the derivative of cos x. Now with these derivatives we can immediately rewrite the Taylor series in this form, that is sin x is approximately equal to sin x star plus cos x star x minus x star minus half sin x star x minus x star. Now remember, x star represents the point about which the Taylor series is being obtained. So the particular expansion you get for Taylor series changes depending on the value of x star. So now we are going to look at the two values which was suggested in the question, that is x star is 0 and x star is pi by 2. So when we look at x star is 0, we take the general equation here which I derived in the previous slide, and we substitute x star is 0 in this equation. So that's the equation here. We can immediately see now that sine of 0 will be 0. So these two terms will essentially vanish. Cos of 0 of course is 1. So sine x is approximately equal to x. That's what I get from this expansion up to the second derivative. Now, of course, if you kept even more terms here, the third derivative and so on, you could get a longer Taylor series for this function. But this particular expansion is valid near x star is 0, and this is often used when we look at small angle approximation, for example. Now let's just consider the second case, that is x star is pi by 2. So again in the general expansion I substitute x star is pi by 2, and then the expansion comes out like this. Now in this case what happens is that the sine pi by 2 term, in two cases this becomes 1 and the cos pi by 2 term becomes 0. That's from trigonometry. So what I get is that sine x is approximately equal to 1 minus half x minus pi by 2 square. So what this particular problem is also telling you is that the Taylor series is a very local phenomena, and the Taylor series of a function keeps changing depending on the point about which you take the Taylor series. So that's something important to remember, that methods which are based on Taylor series are essentially local methods, and therefore they're going to lead to local minima and local roots in any nonlinear equations or any nonlinear optimization problems. Now let's come to question 2, which is expand the following function in a Taylor series about the point 0, 0. So here we have a two-dimensional function. F of x is x1 square plus 2x2 square plus e to the power minus x1 minus x2. Now in many cases I'm just going to leave this x in this form. I'm not going to make it bold, but you understand of course that x here is a vector. In this case it consists of x1 and x2. So what we do is we immediately think about the general Taylor series. Now, if you are interested in the derivation, you can look at my lecture here. I'm going to put the description to the lecture or the theory video in the description box and also in the end screen. So what happens is that we expand f of x. We have the first term here, then we have a term which depends on the gradient vector. We have the second term which depends on the Hessian matrix. So typically these are the important terms which we often retain in Taylor series for optimization problem. There is of course the remainder term which includes all the terms involving third derivatives and so on. Now you remember that C, the gradient, is written in this manner here. So essentially it consists of partial derivatives of the function. Now in my previous tutorial 1 on optimization, we calculated C and H values for this particular function here. And so what I do is that I write the C and H values in green, and then I substitute the value of x star, which I have selected as 0, 0 because that makes life simple. So of course you know that the function value at 0, 0 is going to become 0 plus e to the power minus 0, and e to the power 0 is simply going to be 1. So the function value is 1. Now in this gradient vector C, I put in again x1 0, x2 0. So what I get is these two terms involving just x1 and x2 become 0. And the remaining two terms simply become minus e to the power 0, which is minus 1. So minus 1 comes here. And for the Hessian matrix, again, I have 2 plus 1 here. So that gives me 3. I have 1 here. I have 1 here, and I have 4 plus 1. That gives me 5. So remember, in all these situations, e to the power 0 is simply 1. So I'm making use of the fact there. Now, if you have not figured out how to calculate this, again, take a look at my optimization tutorial 1. Again, I'm going to leave a link to that in the description box and also in the end screen. If I forget to do that, please remind me in the comments below. Now let's write this out. So we had this particular expansion here in terms of the gradient vector and the Hessian matrix. Now I have obtained these matrices here, and I can simply write the function out like this. So you can see in green that fx is going to be fx star, which is 1, and the transpose of the gradient being minus 1, 1 like this, the transpose is going to become a row vector. And then I have x1, x2 here. Remember that x star is 0. So this is only going to give me x1 minus 0 and x2 minus 0. So that's my vector here. And here again you get these particular vectors in terms of the row vector and the column vector. So this is x1, x2, this is x1, x2, and we have the Hessian matrix here. Now, of course, if you are meticulous, you can expand this out, but I kind of like to leave it in matrix and vector form because this is actually a very general form and it lets you see that typical Taylor series can be expressed in this form. Now, if you had a function of even 3 variables, this form would be there. The form would be same, except you would have x1, x2, x3, and so on. If you had a function of n variables, what you would get is that you would get a n by 1 gradient, you would get an n by n Hessian matrix, and you can write this expansion out. Now let's look at question number 3, and this is express the following quadratic form as a symmetric matrix. Now quadratic forms are essentially given in a manner like this, and they are typically given as functions of 1, 2, 3, 4 variables and so on. So this is a simple quadratic form involving only 2 variables x1 and x2. Now, if we take this quadratic form, we can immediately write it in this manner where we put a half here and multiply these terms here in this particular function by 2. And then I can write it out in this form. Now, remember that this is a function involving 2 variables. So I can write it out as x1, x2, x1, x2, 2, 8, 0, 4. Now, if you want to expand it and check it out, you can do that, and you will see that essentially I have a term 2x1 square and 4x2 square. These are the two diagonal terms, and the 8x1, x2 term goes here. And so this I can write as half x to the power t px. Now you see here that this P is an unsymmetric matrix, and the relationship between P and A is there. Again, refer to the lecture here for clarity. So I have P11 is 2, P12 is 8, P21 is 0, P22 is 4, and I also have A12 is A21 is P12 plus P21 by 2 is 4. So what I get is I get a symmetric matrix of this form here. And so that is the symmetric matrix A, which is associated with the quadratic form. So I can write f of x as half xt px, or I can write f of x as half xt ax. Both of these are same. All I have done here is that I have thought of this x 8x1 x2 as 4x1 x2 plus 4x2 x1, and that has let me write this out in this particular nice diagonal form. Diagonal matrices are much more simple to actually study, and you can obtain a lot of interesting mathematical properties from diagonal matrices. Let's come to question number 4, which is that is the following quadratic form positive definite? And you are given this quadratic form here, x1 square plus 2x2 square plus 4x1 x2. Now we take a look at this particular function, and we can immediately write it in this form here. So what we have got here for matrix A is 2, 4, 4, 4. And now you know from the theory of quadratic forms is that if we take this particular matrix and we find the eigenvalues, that's going to tell me more about the nature of this matrix. So that's what I do here. I take the matrix A, 2, 4, 4, 4. The eigenvalues can be obtained by setting this determinant to 0. So I have 2 minus lambda, 4 minus lambda here. And when I solve this characteristic equation, it is going to give me the eigenvalues for this problem. So I do that. This will be 2 minus lambda into 4 minus lambda minus 4 into 4 is 0. And so I get this equation here, which becomes a simple quadratic equation of the form lambda square minus 6 lambda minus 8 is 0. Now, if we solve this particular characteristic equation, we can obtain the eigenvalues of this matrix A, and that's going to tell me about the matrix, whether it's positive definite or not. So let's do that. To solve this particular quadratic equation, I take recourse to the usual formula which we have for solution of the quadratic equation, that is lambda is minus b plus minus root b square minus 4ac by 2a. Now remember here this is in the form ax square plus bx plus c equal to 0. So of course b is minus 6 and a is simply 1 and c is minus 8. So I make those substitutions here in this equation. I simplify it and I get it in this form. And then after some further simplification, this comes out to 3 plus minus root 17, which comes out to finally lambda is 7.123 and minus 1.123. Now, of course, you see here that there is one positive value and one negative value. If it was to be a positive definite matrix or quadratic form, both the lambdas were to be positive. In this case, that has not happened. So A is actually an indefinite matrix and Fx is an indefinite quadratic form. So that's something which we get from this problem. Now let's look at question number 5, which is that is the following quadratic form indefinite? And again, it mentions here that don't use the matrix approach because that's what we did previously. So let's take a look at this quadratic form given here and try to see what is its form or what is its type. Now, if you take a look at this function, you will clearly see that this is a square. And so if I remember the formula a plus b square is a square plus 2ab plus b square, then I can write f of x as x1 plus x2 root 2 square. So let's check out the formula. So this will be x1 square. The second term will give me x2 square into 2, and the third term is going to become 2 into x1 into x2 into root 2. So that's this term here. So now I can look at this f of x and I know that this is going to be positive because this is a square. in almost all scenarios, one scenario I can see where this could be 0 is where x1 and x2 were both 0, for example. In that case, it would still be positive definite. But of course, there is also the possibility that whatever is inside this bracket, this could be 0. So there is a whole set of solutions, x1 plus x2 root 2 is 0, which would actually make this 0. So therefore, this particular quadratic form is not positive definite, it is positive semi-definite. Now, if you want more information on this, take a look at the lecture which goes with this particular tutorial. Now let's come to question number 6, which is again about the previous function we discussed. And we have to look at the same function, same quadratic form, and to show that it is positive definite. And this time we have to use matrix approach, actually positive semi-definite, which we saw in the previous slide. So let's take the function here, and we have written it in this form. So I put the half here. So essentially I had to double all the coefficient terms here. So x1 square became 2x1 square, x2 square became 4x2 square, and this 2 root 2 term became 4 root 2 term. Now, once I get this function here, I can write it out in this form. So what I have got here is that the x1 square term becomes here 2, the 4x2 square term becomes 4 here, and this 4 root 2 term I split into two parts. One will be 2 root 2 here and one will be 2 root 2 here. So I directly get the symmetric matrix corresponding to the quadratic form, and so I can write it as half xtax. And once I obtain this, then I can immediately take the a out, and what I'm going to do now is find the eigenvalues of a. So for that I set the determinant of this particular system to be 0, and once I do that I can simplify it, and you know that for a determinant you have to take this term multiply by this term, that is 2 minus lambda into 4 minus lambda, then minus this term into this term, so 2 root 2 into 2 root 2, this whole thing is 0. Now if we simplify this further, I get this particular expression 8 minus 2 lambda minus 4 lambda plus lambda square minus 8 is 0. So all I've done is expanded this side and expanded this side. So remember here I have 2 into 2, and one more 2 comes from root 2 into root 2. So that is how I get the 8 term here. And once I get this term here, I can simplify it to lambda square minus 6 lambda is 0, because this 8 and minus 8 cancels out. So let's now write this term down. This is very simple. From this you immediately know there are two roots. One of them is lambda is 0 and the second is lambda is 6, because I can of course factorize it as lambda into lambda minus 6 equal to 0. So there are two roots here, and you can see one of the roots is 0. Therefore it's certainly not positive definite, but it is a positive semi-definite matrix. Again, look at the lecture notes to clarify this particular definition. So it's an important point to remember all the different cases you can have in terms of the form of a matrix. You can have positive definite, you can have positive semi-definite, you can have negative definite, you can have negative semi-definite, and of course you have the indefinite case. Now, the most important cases from optimization perspective are typically the positive definite cases. And so those are things which are nice to have, because in that case, the eigenvalues are always positive. But in many cases, unfortunately, we do encounter indefinite matrices, indefinite quadratic forms. And in those cases, we cannot say much about minima, maxima. We need recourse to more information for that. So again, those are things which we have discussed in our further videos. And so some of those problems I'm going to solve in the next tutorial, tutorial 3. So again, today we looked at certain aspects of the Taylor series in 1D and 2D. We saw that the 2D Taylor series could be expressed in the matrix form, because if we have the gradient matrix and we have the gradient vector and the Hessian matrix, we can put things in the matrix form. We also saw the quadratic form and how the concept of the quadratic form leads to the type of a matrix, the type of matrix being very important in terms of positive definiteness, negative definiteness, and so on. And we looked at some particular cases of positive semi-definite matrix and indefinite matrix. Like I mentioned, you take a look at my optimization lecture 2, Taylor series and quadratic forms for the theory, and Take a look at the tutorial 1 in case you did not, for the calculation of the gradient vector and the Hessian matrix for that particular function. And again, take a look at my optimization playlist for the full course. If you have time during your weekends when you are not doing too many things, you can of course look at the optimization lectures to improve your knowledge of this subject, because do remember, it is the bedrock of important subjects, for example data science and machine learning.